Hello, everyone, and welcome to Group 7's presentation on Chapter 15, Analyze Telemetry to Better Anticipate Problems. As an introduction, we will first cover how Netflix used telemetry data to proactively find and fix problems before customers were impacted. Netflix found and fixed problems before it affected the consumer in 2012 by using outlier detection, defined by Victoria J. Hodge and Jim Austin of the University of York. It was defined as abnormal running conditions from which significant performance degradation may well result, such as an aircraft engine rotation defect or a flow problem in a pipeline. Netflix used outlier detection to first compute what was the current normal right now, given population of nodes in a compute cluster, then identified which nodes didn't fit that pattern and removed those nodes from production. Throughout this chapter, we will explore many statistical and visualization techniques, including outlier detection, that we can use to analyze our telemetry to better anticipate problems. This enables us to solve problems faster, cheaper, and earlier than ever, before our customer or anyone in our organization is impacted. Next, we will use means and standard deviation to detect potential problems. One of the simplest statistical techniques that we can use to analyze a production metric is computing its mean or average and standard deviations. By doing this, we can create a filter that detects when this metric is significantly different from its norm, and even configure our alerting so that we can take corrective action. Even if that means we need to alert production staff at 2 a.m. to investigate, it may need to be done. However, when we create alerts that are not actionable or false positives, we've unnecessarily woken up people in the middle of the night. We create better alerts by increasing the signal-to-noise ratio, focusing on the variances or outliers that matter. For example, suppose we are analyzing the number of unauthorized login attempts per day. Our collected data has a normal or bell curve distribution that matches the graph on the slide. The vertical line in the middle of the bell curve is the mean, and the first, second, and third standard deviations indicated by the other vertical lines contain 68%, 95%, and 99.7% of the data respectively. A common use of standard deviations is to periodically inspect the data for a metric and alert if it has significantly varied from the mean. For example, set an alert if the number of unauthorized login attempts per day is 3 standard deviations greater than the mean.
So let's talk a little bit more about this. Now, there are instruments and alerts today that are able to discover these undesired outcomes. And then one of the first things that we need to do is to analyze some of the most severe incidents that have occurred in the recent past. Chances are, if it happened in the past, it will surely happen again. And much like a disease, when you see the symptoms, you can tell what might occur next. So then, in order to figure this out, we would create these lists of telemetries that could enable earlier and faster detections, and then be able to diagnose the problem and resolve it at a faster rate than normal. Now, it doesn't take much to figure out the symptoms of such, and then this can be found in different levels. For example, in the application level, if there was like a sudden increase in web page load times, like that could spell uh, a a potential disaster for the application. Or for the operating system, it could be the server free memory running low or the disk space was running low. That could also trigger an undesired outcome. And within the database level, there it could be like the transaction times could be taking longer than normal. Like if you were ordering something on Amazon and then it was taking about a minute rather than seconds to run the process, then that means something's wrong in the database. Or similar to a network of how there would be a whole number of functioning servers behind the load balancer that it just keeps dropping and then sending it off to some place else to drop more. These signs can be tracked, and they would give us an idea of sort of like an omen that something bad is going to show up, and we need to resolve that quickly. Now, unfortunately, the problems that arise in the telemetry isn't always a is always a non-Gaussian distribution, meaning it's not always a bell curve. As mentioned earlier, um, there would be times like not only would engineers get wake up calls at 2 a.m., but they would also get them later at 2:37 or 4, and then 4:13, then 5:17, and et cetera, et cetera. And this keeps happening when the underlying data that we're monitoring doesn't have that form of distribution. And unfortunately, many of the production data sets are in this style. So it's not always a bell curve per se. There could be like the mean could be at a higher outlier than than normal. So we need to figure out a way to find the certain spot where over alert it doesn't cause an over alert, because that would cause the engineers to be woken up pretty fast. And it's similar to a parent having to watch a kid 24/7. That is not healthy, and it's impossible to function that way. However, if we obtain under alerting, then it could also bring up some significant issues. So the solution to this would be to find the point where it isn't happening all the time, but but not ignoring like some of the other severe issues, so that we would be able to detect the problem fast and then resolve it faster and faster if it keeps on occurring in the future.
Now, we're going to talk about anomaly detection, which is defined as the search for items or events which do not conform to an expected pattern. We can identify the anomalies through our monitoring tools, while we may require help from other people with statistical skills to help analyze the problem later on. It's believed that we can obtain better service quality with an active collaboration between operations and statistics. It's expected that a large percentage of telemetry regarding user data will have periodic seasonal similarities. Things such as web traffic, retail transactions, movie streaming, and many other user behaviors have very regular patterns. This allows us to see situations that vary from what is normal. Because of the usefulness of the techniques that we'll discuss in the next slide, we'll want to seek out people in the marketing or business intelligence departments with the skills to analyze the data. So on to the next slide, where we're going to look at some examples of the techniques. The first statistical technique that we'll look at is called smoothing. It's useful for when the data is shown through a set of timestamps. Smoothing involves moving averages, also known as rolling averages, meaning the transformation of our data by averaging each point with all the other data in our window. This smooths out short-term fluctuations as well as highlights longer-term trends. A second technique we'll look at is called fast Fourier transforms, which is used for image processing. Then the third technique, which we kind of touched on earlier, revolves around the processing of periodical and seasonal data, and then finding the similarities within. This technique is called the Kolmogorov-Smirnov filter. So now on to the conclusion. Through the various techniques discussed in this chapter, we will be much better off at analyzing our production telemetry so we can find and fix problems much earlier, ideally when they're still small and way before they can cause huge problems for us. So we talked about Netflix and the techniques they use to proactively remove compute servers from production as well as auto-scale their infrastructure. Another discussion point we had was the use of the moving average as well as the Kolmogorov-Smirnov filter, which can both be found in popular telemetry graphing tools. So yeah, thanks for watching.